All right. So, greetings, scholars. I think I finally got to the bottom of what was going on with teams. So, when I created a schedule, I told it to repeat every Monday, and then I went back and I told it to repeat every Tuesday, and then I went back and also made another one to say repeat every Thursday. And I didn't realize that creating it that way was going to make two different rooms because I was checking my post. I was like, okay, it's alternating between, one room and the other. Tuesday is one room and Thursday is another. So that's what happened when I created it. I didn't realize it was going to create multiple rooms. So I think we finally got to the bottom of it. I'm just going to kind of let it ride for the rest of the semester. Whatever we've been doing has been working. So, you know, give or take. I'm just going to kind of let it be because I don't want to mess with it and then it goes sideways. Let me see. Only update. I updated the attendance like yesterday, so I don't know if you can check your attendance records or not, but just check and make sure that's in order. Also, it's probably a good idea to keep some kind of documentation or record, like in case you just want to keep your records, your records for yourself, like up to date. So that way, if I like submit something wrong and you want to challenge it, you'll have some proof. As long as you have like some evidence, like, hey, here's a screenshot, I was here for the class, or I submitted that assignment, here's my time sample, whatever. If you have your records on file, if you notice something is out of order, and then that'll suffice to make sure that we get things in order. Now, personally, my personal philosophy for a student that's making an effort, that wants to be here, they're submitting their assignments promptly, I do the best I can for attendance not to be an issue. If they're most of the times when students request, I mark them as excused, as long as it's within reason, as long as it's not like getting out of control or anything like that. As usual, if you have questions, feel free to unmute yourself to get my attention or type in the chat. I am monitoring the chat. Can I see my people? That would be nice. The people not going to show. How do I show? I know there's a way to do it, but I don't feel like fooling with it right now. Oh, let's do this though. That would be nice. Oh, go back. Turn on my captions. That's fine. Cool. Okay, so last week we completed like chapter 7, right? So this week we're going to focus on there's like this alternative set of material. There's an alternate chapter 8. So it's not chapter 8 from our book, but everything is here that you need. And so we pretty much have 5 sections that we're trying to get through for the week. So more than likely, my goal for today, I'd like to get through the first 3 sections of this alternate chapter 8. And depending on how much my energy and how I feel, I might just stay on after I let you guys go and just finish streaming. Yeah. So I'll work that out. But so for right now, let's just kind of hop into the content. Okay. So again, this is an alternate chapter 8. This is chapter 8 from Blitzer Pre-Calculus 5th edition, and it's covering matrices and determinants. All right. It is similar to like the Matrix, like with the Neo, but it's in the sense that the Matrix, as far as the movie, is like a rectangular array, and it's like about a simulation, and this, that, and the other. This is like the background, but to all of that, it's nowhere. It doesn't have a feel like the movie, but it is connected in that sense where we're dealing with rectangular arrays and solving a system of equations. And again, this is the precursor to like a lot of systems that are in play, from like queues and street lights and technology and agriculture, all sorts of different plays, right? So this is like the precursor to that. All right, so chapter 8, again, we're going to get into matrices and determinants, and we're going to start with section 8.1, matrix solutions to linear systems, right? So a few objectives here. We like to write the augmented matrix for a linear system, perform matrix row operations, use matrices and Gaussian elimination to solve systems, use matrices and Gauss-Jordan elimination to solve systems, right? So I think in the last section, in section 7.3, we solved the system of linear equations. So this is an extension of that discussion, where in the previous example, in the previous section, we explored the technique of substitution, where we solve for one variable in one equation and then plugged it into the other, and we solve for the solution to the system. And then we also used a technique last time called the elimination method, where we would get one variable to have the same coefficients but with the opposite signs, add the two equations together and cancel. So this discussion is an extension of that, solving systems of equations, okay? And we're going to get into some somewhat sophisticated techniques, all right? So this is like the undergrad level of linear. It's like linear algebra. Let's get into it. So matrices are used to display information and to solve systems of linear equations. A matrix, the plural being matrices, is a rectangular array. The information is arranged in rows and columns and placed in brackets. The values inside the brackets are called elements of the matrix. Okay. And also, when it comes to attendance, Teams has been successfully taking attendance automatically. So that's what I use to update the attendance. So as long as you get into the team, our meeting for that day, it logs it. And then when I go to update my attendance, I'll see your name and we'll be good to go there. Also, as a request, hopefully, please, I need you guys to show your first name and last name. I have some of you all that either just have a first name and then, you don't want to make it challenging for me to find you. I just need your first name, last name. So then when I'm scanning, I can find you quick and easy and keep it moving. So just make sure that your first name and last name is displayed. So the elements of the matrix are the components, let's keep going. So the first step in solving a system of linear equations using matrices is to write the augmented matrix. An augmented matrix has a vertical bar separating the columns of the matrix into two groups. We have the coefficients of each variable are placed to the left of the vertical line and the constants are placed to the right. If any variable is missing, its coefficient is 0. Okay? So before, we saw a system of linear equations. I think we were working in 2 variables. So now you see we have linear equations in 3 variables, right? So for instance, let me see. Right here. Okay. So let me see. So on the left, we have the system of linear equations. This one is in 3 variables. Whenever we have an unknown, we need an equation, generally speaking. All right. So we have 3 unknowns, x, y, and z. That's why we're given 3 equations. So then to change this system of linear equations into the augmented matrix, first we write the coefficients of our variables, right? You see the 3, 1, 2, 3, 1, 2. You see 1, 1, 2, 1, 1, 2. Uh-oh. We can just suppress you. You are tripping. Why did you switch like that? I don't understand. Pause this. There we go. Probably because I'm on this call. Okay. So in this one, in the second equation system, in the second system, the coefficients we have 1, 2, -5, 1, 2, -5. Notice with the second equation, there's no x, so that coefficient is a 0, then a 1 and 3. 0, 1, 3. And then 0, 0, 1, 0, 0, 1, right? And then the solution, the constants we put on the right-hand side. So you see 31, 19, 25, 31, 19, 25, so on and so on, right? So that's how we rewrite a system of equations in the augmented matrix, right? So that's the first step to solving. Take the system, write it as the augmented matrix with the coefficients and the constants. So a matrix is ones shown along the main diagonal and zeros below the ones is said to be in row echelon form. We use row operations on augmented matrix to produce a matrix in row echelon form. So once we get our system into the augmented form, into the augmented matrix, the next goal is to get it here into this row echelon form. We're going to use these things called row operations. We'll talk about that in just a moment, where through these 3 different row operations, the goal is to get a 1 along the main diagonal and then zeros everywhere below the main diagonal. Once we get it into this form, then the system gets easy to solve. Okay, so let's dive deeper and see what do we mean by row operations. That should be the next slide. Yeah. So matrix row operations. The following row operations produce matrices that represent systems with the same solution set. So we say that these are row operations because we can do these manipulations and preserve the solution to the system. Oh, just a moment. Can I get the screenshot? Oh no. Come on. Yes, that's what I want. Come on. Let me just do this. I'm just gonna close it. Close that. Try that one more again. Oh, we got 5 seconds. No, cancel. That's okay. I got one. That's fine. Okay. I'll send it to my friend later. Yeah, so again, we call these row operations because we can do these manipulation on the entire row and preserve the solution to the system, right? As long as we do these row operations correctly, we don't affect the answer. If we do it incorrectly, then we're not preserving the solution, right? So the row operations are as follows. 2 rows of matrices may be interchanged or switched. This is the same as interchanging 2 equations in a linear system, right? So you can switch one row with another and it'll preserve the solution set. The elements in any row may be multiplied by a non-zero number. This is the same as multiplying both sides of an equation by a non-zero number, right? So the first row operation, we can switch any 2 rows. The second operation, we can multiply any row by any non-zero real number and preserve the solution. And then the third operation, the elements in any row may be multiplied by a non-zero number, and then these products may be added to the corresponding elements in any other row. This is the same as multiplying both sides of an equation by a non-zero number and then adding the equations to eliminate a variable. So like in the last section where we did the elimination method to solve the system, where we would multiply a row by a non-zero number, so that way our coefficients will be the same with opposite signs, and then we add them together to get in a result. That's essentially what we're doing in this third operation. So let's recap these 3 row operations. So the first one, again, we can switch any 2 rows and preserve the solution. Second, we can multiply any row by a non-zero number and preserve the solution. And then the third technique is you can multiply any row by a non-zero number, add that to another row, and replace that row to preserve the solution, okay? So 2 matrices are row equivalent if one can be obtained for the other by a sequence of row operations. Okay, that's fine. Okay, so just to kind of do a quick recap, what we're doing today, this is an extension of solving a system of linear equations. What we're going to do is have a system of linear equations, and we're going to convert we're going to rewrite the system as an augmented matrix. Once we get it into an augmented matrix, then the next goal is to get the augmented matrix into row echelon form, where we have 1s along the main diagonal and 0 everywhere below the 1s. And then, so from there, then we can solve the system easily, okay? So symbols for row operations. Each row operation in the preceding box can be expressed symbolically as follows. If we want to switch any 2 rows, we're going to say like row I switches with row J with a double arrow. If we want to multiply each element in the ith row by k, we can say some non-zero number times whatever row we choose. And then we can add k times the elements in row I to the corresponding elements in row J. So we can say, k times some row added to some other row, replace that second row, right? So let's see this in action. Okay. So we already have this matrix in augmented form, and then we're asked to perform the row operations, switch row 1 with row 2. That one's actually straightforward. All we're doing is switching row 1 and row 2. So row 1 becomes row 2 becomes row 1. I'm not going to write that one. So that means the first row should be 1, 6, -3, 7. You see it here. 1, 6, -3, 7. I think I said the wrong thing, but right? And then, so all we did there was switch row 1 and row 2. Okay. Using this matrix, now they want us to say 1/4 times row 1. So we're basically multiplying row 1. We're distributing 1/4 into row 1. So then that's going to become 1, 3, -5, 2. You see it here. 1, 3, -5, 2. Okay. Okay, so hopefully we're all aboard and we're not all bored. If you have questions, feel free to unmute yourself to get my attention. Let me check the chat. Definitely, I was distracted earlier a little bit. It should be, there it is. I think the chat looks good. Okay, let's keep moving. Okay, so this one is the third technique. This is asking us to say 3 times row 2 added to row 3, replace row 3. So then that would be 3 plus -3. So the first entry in row 3 would be a 0. 18 minus 2, so it would be 0, 16, -8, and then like negative, and then 20, then 12, I think. Right? 0, 16, -8, and 12. You see it here. I'm trying to get to an example where we get it into row echelon form so I can write it out. Let's keep going. So solving systems of 3 equations with 3 variables using Gaussian elimination. Okay, so write the augmented matrix for the system, and then use matrix row operations to simplify the matrix to row equivalent matrix in row echelon form with ones along the main diagonal for upper left to lower right, and zeros below that main diagonal of ones. And then write the system of linear equations corresponding to the matrix in step 2, and use back substitution to find the system solution. That's kind of a mouthful. Again, I feel like that becomes evident when we work in examples. I'm just trying to get to an example. Use matrices to solve the system. Okay, this is a good one. I feel like we need some space. This is 17. Let me get a blank page. So let's copy. I gotta wait until it says paste because it'll be taking a sweet time. Copy. Oh, come on, you can do it. I believe in you. We're on 17. That should be enough time. There it is. Paste. Let me do one more. Just giving myself some blank paper. Okay. So first objective is to write this system in augmented form, right? So we just basically take the coefficients. So then we have 2, 1, 2, 18. We have a 1, -1, 2, 9, 1, 2, -1, 6. Okay. So this is that linear system in augmented matrix form, right? So the next goal is to use the row operations. We want to get a 1 along the main diagonal. So we want to transform all these guys into a 1 and then use those ones to get it 0 everywhere else. But each step is through a row operation. So first, let's get a 1 in this position. And I think I'm going to do that. I'm going to switch row 1 and row 2. Okay. So I want row 1 to switch places with row 2. Okay, and I'll put the result over here. So now my row 1 is going to be 1, -1, 2, 9. My row 2 is now going to be 2, 1, 2, 18. And my row 3 is 1, 2, -1, and 6. Okay. So now we successfully achieved our first goal of getting a 1 in this position. Notice we already have a 1 in this position now. So then now let's go ahead and get a 1 in this position. And we can get this to we can get this final one to a 1 by multiplying row 3 by a negative. So we're going to say basically a -1 times row 3. Replace row 3. Okay. So with that, that means row 1 stays as is. Row 2 stays as is. And now row 3, we're distributing a negative. So that becomes -1, -2, 1, and then -6. Okay. All right. So now we've gotten our 1s along the main diagonal. So now we're going to continue to use row operations to transform this. We call this a lower triangle. We want to transform that to all zeros. Okay. So I'm going to cheat a little bit and kind of do multiple steps in one go. So I'm going to use this one and that third technique to transform both of these guys to zeros. So for instance, if I want to change row 2, I'm going to say -2 times row 1, add it to row 2, and I'm going to replace row 2. Okay. Also, let me get rid of that. I'm going to do a second one, and I'm going to change row 3 as well. So I'm just going to say row 1, add it to row 3. Again, I'm going to replace row 3. So I'm going to just do those together. And I kind of want to keep working here because I think I have space. I am going to shrink this down just a little bit to give myself just some space. That's decent like that. Okay. As a matter of fact, I'm going to take it a step further. I'm going to move these guys just because I can. I'm just doing this because I can. Move that there. Matter of fact, undo, undo, undo. Yeah. I'm just going to move all of this like right here. Just use it as a reference for now. Okay. So now that gives us some space to keep going. Okay. So now with those row operations that we just introduced, the only row 1 stays as is, right? So we're only changing row 2 and row 3. So row 1 is 1, -1, 2, and 9. Now row 2, we said -2 times row 1 plus row 2 replace row 2. So that means this is going to be a 0. 2 plus 1 is 3. -4 plus 2 is -2. Oh no, I forgot that would change. Okay, that's fine. Well, we'll have to fix that. We'll fix it. I did it in the wrong order, but that's okay. We'll adjust. Let me see. That's going to be a -18 plus 18 ends up being a 0. And I think our other one might change as well, but that's okay. We'll fix it. So then now we want to say row 1 plus row 3 replace row 3. So 1 plus -1 is 0. -1 plus -2 is -3. 2 plus 1 is 3. 9 plus -6 is 3. Okay. So, oh, nope, cancel. All right. So yeah, I forgot I did it a little bit out of order, but that's okay. So now we have our one. This column is set, so that one is not going to change anymore. What I'm going to do, I'm going to multiply row 3 by a -1/3. That one looks like it's easier to get to a 1 than row 2. So I'm going to say a negative. I'm going to say a -1/3 times row 3, replace row 3. I'm just going to go ahead and do the next step as well. I'm doing that so that the next step I will do will be, I want row 3 to switch places with row 2. So I am kind of cheating a little bit here. We don't usually do it like this, but this is fine. So now if I say a third times row 3, sorry, a -3rd, and if I go ahead and do the switch, let me see, row 1 stays as is. Okay. Now my row 3 would be 0, and then what is that? A +1, a -1, -1. But instead of writing it row 3, I went on and switched it with row 2. So then row 2 is now down here. Okay, I feel like we're okay so far. So first I got a 1 here, then I got zeros below it. Now I got a 1 here. I'm going to use this 1 to get a 0 everywhere else in that column. Okay. I feel like we're okay. So now, if I say, let's do row 2 plus row 1 replace row 1. And then also let's do -3 times row 2 plus row 3 replace row 3. Okay, I think we're almost there. Okay. So now row 2 plus row 1 replace row 1. So that means this preserves our 1 there. That becomes, oh, my bad. Let me back up. I'm doing a different technique. I'm getting a little ahead of myself. Let me back up. I'm giving us extra steps. Instead of doing that, let me back up one. Just realized. So I forgot. Our original goal was to get row echelon. So I don't need the right now I don't need the 0 here, right? I was trying to get that to 0. I forgot we don't need that just yet. So we're going to use this 1 to get a 0 below it. So then we'll just do -3 times row 2 plus row 3, replace row 3. Okay. All right, that's better. So now that means row 1 stays as is, 1, -1, 2, and 9. Row 2 stays as is, so that's a 0, 1, -1, -1. And now row 3, so 0 plus 0 is 0. -3 plus 3 is 0. 3 plus -2 is a 1. Ding, 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 ding. 3 plus 0 is 3, right? That's the goal that we wanted. So again, as long as you do your row operations properly, you won't change the solution. Hopefully we can do another one so I can like be more precise and not have all the extra steps, right? But this was the goal. We got our 1s along the main diagonal, and then we got this 0s in the lower triangle, right? So then from here, what this is saying is that, what this means is that z equals 3, okay? If we use row 2, that's saying y minus z, so that's going to be y minus 3, equals -1. So then y equals 2, okay? We got our z, we got our y. And then from the first row, we're saying that says x minus y, so x minus 2 plus 2 times z, so that's a 2 times 2, equals 9, right? So column 1 refers to the x, column 2 refers to our y, and column 3 refers to our z, right? So we have one equation, one unknown. Let me see. 4 minus 2 is 2. If we subtract 2 on both sides, we get that x equals 7, okay? So our claim is that the solution to the system is going to be what? X equals 7, y equals 2, and z equals 3. Now, I thought I was going to need more space. And if I had done it the right way, I could have saved, I wouldn't have needed as much space, but that's okay. You know, I have to dust off the cobwebs. Okay, so we're here, right? So now, we want to check this, right? How could we check this? Basically, just plug in those x, y, and z and make sure it makes each equation true. So then 14 plus 2 is 16 plus, let's see, did we miss something? Maybe we made a mistake somewhere. Z is 3. Let me see, y minus z. So then y minus 3, if we add, that's a 2. Oh, okay. Let me check it again. Let me see. That's a 14. 14. Nope, it's not working out. 14 plus 2 is 16. That should be 22. So something's off. Okay. X is 7, 2, and 3. Okay. I might just start over. Something got off somewhere. I did a calculation wrong somewhere. 2, 1, 2, 18. 1, -1, 2, 9. 1, 2, -1, 6. That looks good. Okay, let me just try it one more time. I don't feel like, because I know I made some mistakes, I'm just going to redo it. But it should go a lot faster because, you know, let me just try it one more time. Something's not working. So here, let's do this. All right. So our coefficients, 2, 1, 2, 18, 1, -1, 2, 9, 1, 2, -1, 6. Okay, I feel like that looks good. So the first goal is to get a 1 in the upper left. Let's, we can just switch 1 and 2. So we'll say row 1 switches with row 2. Okay, so then that becomes 1, -1, 2, 9, 2, 1, 2, 18, and then 1, 2, -1, 6. Okay, so then we're going to use that 1 to get zeros. We're going to use this 1 to get zeros below. So then we can say -2 times row 1 added to row 2, replace row 2. And then we can also say a negative times row 1, added to row 3, replace row 3. Okay, let's do this. Right here. Okay, so that means row 1 stays as is. 2, 9. Okay, so negative 2 plus 2 is 0. 2 plus 1 is 3. Negative 4 plus 2 is negative 2. Negative 18 plus 18 is 0. Okay. And then negative 1 plus 1 is 0. 1 plus 2 is 3. Negative 2 plus negative 1 is negative 3. Negative 9 plus 6 is negative 3. Okay. So that, I think we had this before, but I just want to do this. So we got our 1 with our zeros. I want to switch row 2 and row 3. Let me just do it in 2 separate steps. Well, here. So basically what I'm doing, I'm going to say row 2 switches places with row 3. Okay. And then after that, I want to say the new row basically is going to be row 2. I want to say, no, cancel. I'm going to say a 1/3 times that row 2. So after I switch it. So I'll say a 1/3 times row 2, replace row 2. Okay. Let me give myself some space. I'm just going to shrink this down to here. Okay. So then essentially what I'm doing, so my row 1 stays as is, 1, negative 1, 2, and 9. Okay. Now if I switch row 2 and 3 and then I distribute a third, I'll get a 0, 1, negative 1, negative 1. And my new row 3 should be 0, 3, negative 2, and 0, because we didn't make changes to that. We just changed the position of it. Okay. So now we want to use this 1 to get a 0 below. Okay. So what I'm going to do, I'm going to say a negative 3 times row 2, added to row 3, replace row 3. Okay. So that means row 1 stays as is. Row 2 stays as is. Okay. And then row 3, so that stays as 0. That becomes 0. 3 minus 2 is a 1. 3 plus 0 is 3. Okay, so it looks like we got a similar result. So now from here, this says that z equals 3. Okay, so that's one result. And then from the second row, that says y minus z, so y minus 3 equals a negative 1. If we add 3, y equals 2. I think that's the same result. Okay, so then with this first row, we're saying x minus y, so x minus 2 plus 6 should equal 9. Okay, I think this is where, I think this is where we made our mistake before. So that's a 4. If we subtract 4 on both sides, it looks like we get x equals 5. Okay, there, that's better. Okay, I think we got, let's try this one. Let's see if it works. So now our claim is that x equals 5, y equals 2, and z equals 3. Again, let's check this. I'm going to cross the fingers. If I don't get it right this time, then, I'll probably just use my notes. Okay, let's go with it. So now, 10 plus 2 is 12, plus 6 is now 18. So that it checks out in the first one. The second one is 5 minus 2 is a 3. 3 plus 6 is 9. That one checks out. 5 plus 4 is 9. Minus 3 is 6. Okay, so I think what we had before was good. It's just we made a mistake with the x, right? Because we got the same z, we got the same y, but somehow our x, that first row got off, right? And instead of, I could have gone line by line to try to get to the bottom of where we made the mistake. I was like, well, let me just redo it. I just felt like redoing it, right? So, but we finally got to a solution. So we got 5, 2, and 3. Oh, I did add blank pages. I don't need this, guys. Delete. and delete. Okay. All right, so here's a type version of what we experience. We take this linear system, write it in the augmented matrix form, and then through a row operation. So they switched 1 and 2. I think that's what we did as well. And it won't necessarily be the same like options because we could have switched 1 and 3. As long as we apply the row operations properly, then it's kind of dynamic. It's not set. It's like it's multiple ways of getting to the solution, right? But we should get to the same solution, right? Okay, 5, 2, and 3. I think that's exactly what we got. Okay, that was an adventure. Let's keep going. So solving a system using Gauss-Jordan elimination. To write the augmented matrix for the system, use matrix row operations to simplify the matrix to a row equivalent matrix and reduce row echelon form, with ones along the main diagonal from upper left to lower right and zeros basically in a lower triangle. Okay, so that's kind of writing out in words what we experienced together. We got a 1 in the upper left. Use that 1 to get zeros in the rest of that column. Then get a 1 in the center. Use that 1 to get a 0 below it, and then try to get a 1 in that final position, the lower right hand position. And then use the reduce row echelon form of matrix of the matrix in step 2 to write the system solution set. Back substitution is not necessary. Okay. So this is another one. Maybe I can paste that page. I might need it. Maybe I should take advantage of this time. Paste. Okay, that looks good. All right. So let's write the system in augmented matrix form. So first we just need the coefficients. So then we have 2, 1, 2. Is this the same thing? 18. Wait a minute. I think it is the same. So 2xy plus 2. Okay. So with that being the same thing, we can actually take our solution that we had in reduced row echelon form. So we can actually start here, right? Let me get a copy of this. So instead of doing those row operations again, we can actually just start off here in this reduced row echelon form, okay? So Gaussian takes it further, which is what I was trying to do originally. We paste, and let me get rid of this. Delete. I think these are the same, right? Okay, so we're just gonna pick up here. So then to do Gauss-Jordan, basically all it is, we got this lower triangle to be zeros. Now we just want to get this upper triangle to be zeros. Once we get the lower triangle to be zeros and the upper triangle to be zeros, that'll be, then the answers are just going to be apparent, right? So now that we got it in this form, we can use these ones to get zeros everywhere else. So let's start here. Let's use this 1 to get a 0 above. So then what I'm going to do, I'm going to say row 2 plus row 1. I want to replace row 1. Okay. So then 0 plus 1 is 1. 1 plus -1 is 0. -1 plus 2 is 1. -1 plus 9 is 8. I think row 2 stays as is. And row 3 stays as is. Okay. So we got our desired 0. So now what we'd like to do is use this 1 to get zeros everywhere above it. Okay. So I'm going to say a negative times row 3 added to row 1, replace row 1. And then also I'm going to say row 3 plus row 2, replace row 2. So these are the operations that I'm doing. Okay. So then 0 plus 1 is 1, 0 plus 0 is 0. -1 plus 1 is 0. -3 plus 8 is 5. Okay. And then row 3 plus row 2, so that's a 0, that's a 1, that's a 0, that's a 2, and then row 3 stays as is, 0, 0, 1, 3. Okay, so then in this form, this tells us the answer right away. We don't have to do any back substitution, right? Because this basically says what? X equals 5, Y equals 2, and Z equals 3, right? That's what I was trying to do originally, is get to this form. So in the previous example, we got it into reduced row echelon form where we had ones along the main diagonal and zero in the lower triangle. And then we use back substitution to solve. Well, with Gauss-Jordan, once we get the coefficient matrix to, that's basically called the identity matrix, where we have ones along the main diagonal and then zeros everywhere else, then the answer is just shown on the right-hand side in that constant matrix, right? That's our solution matrix. Okay, so the Gauss-Jordan just takes that first technique that we did, and it just gets that upper triangle to be all zeros. Okay, hopefully that makes sense. You know, let's see what else we have. Right, so we got the same result. We didn't need that paper. We didn't need that page, so we can delete that. Okay, so we started with the reduced row echelon form from the previous example, and then use row operations to get basically. That's the Gauss-Jordan, one along the main diagonal and zero everywhere else. So then it tells us the solution right away. Okay. All right. So that was 8.1, right? Basically taking a linear system of equations, rewriting it as an augmented matrix, and then using row operations to get it to either reduce row echelon form or using Gauss-Jordan where you take it a little bit further.